Okay, so right now we're going to talk about matrix equations. So we talked about this in class a little bit, but just to get more formal. So if A is an n by n matrix with columns, right, so A1, A2, and so on up to AN, so each of them are in Rm, right? So if we think about what is the rows are kind of the dimension of each column vector. So if x is a vector in Rn, right, then the product Ax is the linear combination of the columns of A using the entries of x as weights. Right, so what we're saying is like Ax means that I've got the first column times x1, the second column times x2, and so on. And this is a lot like what we've seen. So for example, if I have A is equal to 1, 2, 0, 3, negative 1, 0, and x is 1, 2, negative 1, then Ax is going to be, right, A times x, which is, right, 1 times 1, 2 plus 2 times 0, 3 plus negative 1 times negative 1, 0, right? So it's kind of, so to get 2, right, 1 plus 0, right, plus 1, which is 2, and 2 plus 6 plus 0, which is 8. Right, so if we're thinking about this, this kind of gives us room for the representation. So this is essentially the same setup we had before. Right, so A is an m by n matrix with n columns in Rm. Now B is in Rm. Right, so the following things have the same solutions. Right, so the matrix equation Ax equals B, right, so if I think again about my entries x, like I'm trying to find that, I can also think about it as the coefficients that make up the linear combination that adds to B. Right, so we've used C1, C2, and so on here, but this time x1, x2 just for consistency. Right, and the linear system with the augmented matrix AB. Right, so you can really sort of see the similarities here. And right, so we've gotten really comfortable working with these two and done some stuff with this, but we just want to bring it into the mix because this is really what we're going to use for linear transformations. And it's important to note here that, right, when I say the same solutions, right, that doesn't mean that they're exactly the same thing. The fact that these different things all can kind of be transformed one into the other and have the same solutions is pretty powerful, but they can come about from entirely different scenarios. It's sort of like if I said my current math class is linear algebra. Both of those things are referring to the same thing. So you could in some sense say that they're the same, but if I said my current math class is my current math class, right, those are literally the same words, and those are not, you're not really getting any information there, right? So they refer to the same object, but not necessarily exactly the same. Okay, let's talk about matrix operations. All right, let's talk about matrix operations. So let A be an m by n matrix, right? And we're going to kind of use subscripts to be a little more general here. So A11, A21, A31, AM1, right? And then going across, I'm increasing the second entry. So you can kind of see that my subscripts are going in order with the m by n matrix. So the first one is my rows, the second is my columns. So you can see the second entry is increasing here, first entry is increasing here. So if m equals n, then we say A is a square matrix, n by n. And we've seen that before. So the diagonal entries of a matrix would be, well, the ones on the diagonal, but formally 1, 1, 2, 2, up to n, n. And we want to talk about that because a square matrix whose non-diagonal entries are 0 is a diagonal matrix. right? So you can see an example here, right? I've got 0, 1, 0, 0, 0, 7, 0, 0, 0, negative 5. You can sort of see, right, all my entries not along the diagonal are 0. Now, a square matrix with zeros above or below the diagonal is called an upper or lower triangular matrix, right? So in this case, A, notice that above my diagonal entries 1, 4, 6, I've got 0, 0, 0, right? So you can kind of see how this forms a triangle, and this would be lower triangular. Okay, let's talk, so we kind of needed to get that vocab out of the way. Let's talk matrix addition. To add two matrices together, add their corresponding entries. So the way that you'd say that is, right, A plus B is equal to the matrix made up of Aij plus Bij. Right, so all my corresponding entries are added. So like here you can see 1 plus 0 is 1, 2 plus 1 is 3, 1 plus 1 is 2, and 3 plus 2 is 5. I almost said 4 here. It's a good thing that I'm not putting this on the internet. It would be embarrassing if a math teacher mixed this up. Then again, mistakes happen. Okay, scalar multiplication. We've seen this a fair bit, but I just want to emphasize that it works for higher and more irregular matrices beyond just vectors. So if A is an m by n matrix and C is a scalar, then the scalar multiple CA is CAIJ, which, right, C gets pulled into the matrix C times AIJ. So if I've got 2 times the matrix 1, 2, 3, 4, then I've got 2, 4, 6, 8. Right? I just multiplied each corresponding entry by 2. Okay, let's talk about matrix multiplication. If A is an m by n matrix and B is an n by p matrix, meaning they don't have to be the same dimension, but notice that, right, my columns here have to match up with my rows here. And B has columns, right, B1 and so on up to BP. Then the product, AB, is A times B1. And then think about that. So what this is saying is like this is a column, and that's a column, and so on, right? And so essentially what's happening is I'm saying if I have, say, a larger matrix, right, then it's sort of like I'm thinking about just multiplying this vector times the matrix to get one of my columns, and then multiplying this vector times the matrix to get my second column. Right, so if AB is equal to this times that, right, so this is going to be one column, and that's going to be one column, right? And you can see that that's 3, 1, 2 comes from this 3, 1, 2, right? And 1, 0, 2, 1, 0, 2. Right, so it's like I just, kind of like I just, worried about sort of thinking about like this matrix, or this vector times the matrix, and then this vector times the matrix. And so if I add those up, just like I did when I'm talking about the product AX, right, this is 1, 5, and this adds up to negative 3, 6. And so again, just to note, like the ith column of AB is a linear combination of the columns of A using the weights from the ith column of B. Right? So the first column of AB is a linear combination of all the vectors in A using the weights from the first column of B. Right? And then the second column of A, AB uses the second column of B as weights. And the book here has a different way of solving it, where it kind of talks about doing something like going here and then down and then doing that. And so like that, these two would end up giving you your first entry here, right? And like if I went and then if I went blue and here, right, that would give me my second entry, and so on. The only reason to do that is as you get into larger matrices, it becomes easier, right? This, I think, makes a lot more conceptual sense, but it can be harder to write, right? Or just kind of not harder, but cumbersome to write down. And so if you're just kind of adding series of numbers in your head, like your products, so 1 times 3, 2 times 1, and so on, you can kind of see that that's what's happening here. But it makes no conceptual sense, and it's just like a shortcut. So I'm not going to really use it in class. It is in the book, like I said, if you want to go see how it's done. But I will encourage you at the beginning kind of enforce this as a way of multiplication, because this is the one that kind of makes sense in terms of connecting back to everything that we've already done. All right, but that's it. That should be enough to move forward and set the stage for what we're going to do in class next.